Prepare yourselves, fellow rock enthusiasts, for a deep dive into the fundamental geological concept that explains why our planet isn't just a static ball of rock, it is a constantly shuffling a deck of massive lithospheric plates. These materials offer a solid introduction to the theory of plate tectonics, which is essentially our global model for explaining the movement of the Earth's crustal plates. The Earth, it turns out, is far more dynamic than many might initially realize. The movement occurring at the edges of large, rigid slabs of its outer shell accounts for many dynamic surface features like mountain building, volcanic activity, and perhaps most famously, earthquakes. So, what exactly are these moving slabs? The sources explain that the rigid outer shell consists of the crust and the upper mantle. This combined layer is called the lithosphere. Beneath the oceans, this lithosphere is about 100 kilometers or roughly 62 miles thick, while continental crust alone can be 35 to 60 kilometers thick, about 22 to 37 miles. The lithosphere is described as relatively cool and rigid. This rigid shell is not one solid piece but is broken into a dozen or more plates. These rigid plates don't just float in a void. They lie on a deeper layer called the asthenosphere. The asthenosphere is characterized as a weak, high-temperature plastic layer. Its key property is that it's capable of plastic deformation and can flow slowly. It is this slow flow in the asthenosphere that allows the rigid lithospheric plates resting on top to move. The distinction between the lithosphere and asthenosphere is based on their different mechanical properties and how they transfer heat. The lithosphere is rigid and loses heat by conduction, while the asthenosphere is softer, hotter, and transfers heat by convection, possessing a nearly adiabatic temperature gradient. It is crucial to keep in mind that this is a mechanical division and shouldn't be confused with the chemical layers of the Earth, the crust, mantle, and core. The mantle, for instance, spans both the asthenosphere and part of the lithosphere. And for completeness, let's remember the Earth's core, the central zone where the Earth's magnetic field originates. This magnetic field will become quite important shortly. The modern theory of plate tectonics stands on the shoulders of earlier ideas, most notably continental drift. Proposed by Alfred Wegener, a German meteorologist, continental drift suggested that continents moved great distances across the ocean floor. Wegener wasn't just spitballing. He presented substantial evidence, including the striking similarity of coastlines, shared fossil records, and matching geological structures across continents now separated by vast oceans. Imagine matching up puzzle pieces after millions of years. That's essentially what Wegener saw. However, despite this compelling evidence, Wegener's hypothesis wasn't widely accepted initially because he couldn't fully explain how the continents moved. The prevailing view at the time was that ocean basins were fixed and in a locked position. The missing piece of the puzzle began to fall into place with the concept of seafloor spreading. This idea emerged from extensive ocean floor exploration in the 1950s and 1960 seconds, which revealed vast linear mountain ranges beneath the waves, identified as mid-ocean ridges or spreading centers. Seafloor spreading is the process by which new oceanic crust is continually formed along these ridges. Magma, hot molten rock generated within the Earth, rises up along these linear belts, is extruded and intruded, and cools to form new crust. This new crust pushes the older crust away from the ridge axis. The spreading is more or less symmetrical, adding crust to the plates on either side at comparable rates. Crucially, the process of seafloor spreading provided powerful evidence for plate tectonics through the phenomenon of magnetic stripping. As the molten rock cools and solidifies at the mid-ocean ridges, magnetic minerals within the rock align themselves with the Earth's prevailing magnetic field. The Earth's magnetic field isn't static. It has periodically reversed its polarity throughout geological history. Scientists established a geomagnetic timescale, a chronology based on dating these reversals by examining young volcanic rocks. When combined with the idea of seafloor spreading, these magnetic reversals explain the symmetrical pattern of magnetic anomalies or magnetic lineations observed in the oceanic crust on either side of the mid-ocean ridges. These lineations are local variations in rock magnetization reflecting the direction of the Earth's magnetic field at the time the rock solidified. The perfect match of the magnetic stripe pattern on opposite sides of a ridge and its correlation with the known geomagnetic timescale strongly supports the idea that new crust is being created and moving outwards. The movement of these lithospheric plates isn't just about creating new crust. It's also about how plates interact along their edges, forming different types of plate boundaries. These boundaries are where most of the Earth's significant geological events occur. The sources highlight three main types. 1. Divergent boundaries. These are where plates move apart. Mid-ocean ridges are the classic example, fueled by seafloor spreading. Earthquakes at these boundaries are common but are typically shallow, less than 30 kilometers depth, and confined to a narrow zone near the ridge. 2. Transform faults. Here, plates slide past each other horizontally. The San Andreas Fault in California is a well-known example. Like divergent boundaries, earthquakes along transform faults are shallow. These boundaries probably invented passive-aggressive behavior in geology, just silently sliding past each other, occasionally throwing a quake tantrum. 3. Convergent boundaries. This is where plates move towards each other. One common type is a subduction zone, where one plate dives beneath another. Subduction zones are geological hotspots, though not the hotspot kind. Confuse not. They are characterized by a very high abundance of earthquakes, which increase in depth on the landward side of the boundary. These zones are also sites of significant mountain building and volcanic activity. The worldwide distribution of earthquakes is a direct consequence of these plate boundary interactions. The vast majority of seismic activity occurs along the margins of the moving plates. Understanding the different types of boundaries helps explain the characteristics of earthquakes observed in different regions. For instance, the deep earthquakes characteristic of subduction zones differ from the shallow quakes at ridges or transform faults. Moreover, large earthquakes occurring offshore can generate dangerous tsunamis, emphasizing the importance of understanding plate tectonics for hazard mitigation. Modern geologists aren't just relying on seismic records and magnetic maps. Technology has given us fresh eyes on plate movement. GPS Global Positioning System is a powerful tool used in earth sciences, enabling scientists to monitor how landscapes move and change shape over time. GPS is used to determine how far the ground has moved during earthquakes and can also monitor other dynamic features like landslides and volcanoes to help issue warnings. For example, hundreds of high-accuracy GPS receivers are permanently installed across the San Andreas Fault in Southern California, specifically to monitor earthquakes and tectonic plate motion. So, yes, GPS is tracking your pizza delivery and the slow march of California towards the Pacific, multitasking at its finest. Scientists can download and analyze data from these sites, like P499 on the San Andreas Fault, to explore ground movements. The sources also touch upon areas of ongoing research and debate, such as the nature of hotspots. While conventionally linked to deep mantle plumes, the sources mention that there's insufficient evidence to prove plumes originate from the core mantle boundary. An alternative perspective suggests that the volcanic activity attributed to hotspots might instead arise from weaknesses. Scars from past events like collisions or divergence within the tectonic plates themselves, where they pass over easily melting subducted material under reduced pressure conditions. This reminds us that even well-established theories are constantly being refined and challenged as new data emerges. Always keeps things interesting. Ultimately, studying plate tectonics and related processes like seafloor spreading isn't just academic. It has significant practical applications. Many of the world's geologic hazards, which pose dangers to human life and infrastructure, are direct results of plate movement. By understanding the distribution of earthquakes and volcanoes, knowledge gained from studying seafloor spreading can help scientists and government agencies work to reduce the potential damage from these events. It's about appreciating the incredible, sometimes volatile, dynamics of our planet, from the creation of underwater mountain ranges at spreading centers to the destructive power unleashed at plate boundaries. In conclusion, these materials provide a robust overview of plate tectonics, rooted in the structure of the lithosphere and asthenosphere, tracing its historical development from continental drift to the acceptance of seafloor spreading as a driving mechanism. They highlight the crucial evidence from magnetic lineations and the distribution of earthquakes, which are directly linked to the different types of plate boundaries. Furthermore, they point to the role of modern technology, like GPS, in monitoring plate movements and the practical importance of this knowledge in understanding and mitigating geological hazards. It's a testament to how far geology has come, from puzzling coastlines to precisely measured plate velocities, all thanks to Earth's relentless and occasionally shaky tectonic dance.
My name is Ricardo Valls. I am a professional geologist registered in the province of Ontario, Canada, and also the president of Valls Geoconsultant. Geology, geochemistry, structural analysis, machine learning, and artificial intelligence. I am sure you will find something useful among my over 550 videos.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.